Okay, so let's get started. Now, today we are very happy to have Fengwei from University of Florida talk about stability of superconducting strings.
Thank you. Yeah, thanks for the invitation. And today's the talk is based on a recent study with my collaborator K in the audience, and also a student at UF, a tutor and Professor Wei Xue. And the talk is about the stability of superconducting strings. So first, I will try to explain why the cosmic string is superconducting. And then I will move on to talk about the stability problem. That actually is an open question in the literature for past 4 decades. And the interesting thing is if you conduct the string is superconducting, when you form the string closed string loops, this superconducting string loop can give you a stable configuration called the vorton. And this vorton can form at a very early time. And if the vorton is stable enough, for example, the lifetime can be the age of universe, then it may be very interesting. Then we may even ask whether the vorton can be dark matter. So therefore it's very important to study the stability of this superconducting string. On the other hand, this stability problem is very complicated because it depends on both the string dynamics, for example, the string loop contraction and radiation, and also it also depends on the fermion DMO propagating along the string. In this talk, I will focusing on the fermionic superconducting string, where the fermion DMO propagating along the string as charge carriers. So we also need to care about the dynamics of this fermion DMO inside the string. And these dynamics can be classified into decay process, counterling, and scattering process, with some diagrams shown on the right-hand side. In this talk, I will try to explain all of them together. First, let me introduce cosmic string to you. And here I choose one simple example. It's called axion string. And the theory is just a complex scalar field with a U1 global symmetry, where the potential of this complex scalar field described by the Mexican head potential, where lambda is the self-coupling of this scalar, and VA is the only energy scale show up in this theory, which is a symmetry breaking scale. So when the U1 global symmetry is spontaneously broken, you can see the phi field will rise on top of the Mexican head to the new vacuum and pick up a random phase. In the trivial configuration, the phi is just given by a non-zero vacuum expectation value, which is VA over square root 2, and it's a constant. Then it's a trivial configuration. And on the other hand, when you consider in one Hubble patch, there can be many different coherence region of the phi field. In different coherent region, the phase angle of phi are uncorrelated. And if it happens to have some non-trivial widening of this coherence region, then you find some cosmic solutions in that Hubble patch. And this is given by Kibble mechanisms. And on the left-hand side, I show a cartoon of some open string segment. And let's focus on the transverse plane with rho theta, the polar angle of the coordinates. And here below, I show the asymptotic behavior of this complex scalar field configuration phi. If you first look at the asymptotically far region, you find the amplitude of phi field reach to the constant value given by the web. And the phase angle, it goes like the azimuthal angle of theta. When you are close to the string center, to avoid the singularity, you need to make the amplitude phi vanish. And if you further integrate over the energy density on this transverse plane, you can define the string tension mu. And by dimension analysis, it's dimension 2, so it's proportional to the v square. And also it has a famous logarithmic divergence coming from the gradient term of the phi field. And also it depends on both the IR cutoff L, the separation of the two long strings, and also the UV cutoff delta, which is determined by the core size, basically inverse of the scalar field mass. Okay, now if we introduce...
So your phi is periodic or is not periodic?
Phi is basically
It's just a standard complex field?
complex field configuration where the energy is minimized, something like that. So you can solve the equation motion of the phi and find this classical configuration.
So the zero mode is a periodic scalar, but phi itself is not a.
Yeah, phi is not. Yeah.
The axion doesn't have mass here.
Axion here is massless. Yeah, I didn't choose different. Yeah, there's no cosine potential here. It's just a very general U1, yeah, scalar field.
What was L in the string tension?
Oh, L is the separation of two long string that give you some IR cutoff.
But delta is your cosines?
Yeah, delta is the cosine, the width, yeah. Yeah, UE cutoff. Okay.
Yeah, if you actually do the integral over a transverse plane with one string, it's just divergent, right?
Yeah, it's divergent, the log, and so you need some cutoff, like the Hubble size or separation. Now let's introduce fermion to the story by simple Euclid coupling with this phi field. Then we can solve the equation motion of the fermion per psi. And in the trivial configuration, when phi is given by this constant depth, you find the second term of this equation motion just a usual mass term for this fermion. Then you find the solution is a simple plane wave solutions. And here I just give you some ultravativity limits. The spinor wave function depends on proportional to this spinor eta. And here I choose the propagation of the fermion along z axis. So you can have this simplified spinor results. However, if you go to the string background and solve the same equation of motion again, you find the solution change. First, I parameterize the string as a straight string along the z-axis, and I introduce this f rho. It's called a string profile function, which gets the value from 0 to 1 when the rho changes from 0 to infinity. That just tell you the asymptotic behavior of the string. And then the per psi can be solved by using separation of Weibull methods. You separate the longitudinal direction and transverse direction and define these two wave functions. And first, let's focus on the transverse directions. You find this equation motion in the transverse directions reduced to a stationary Schrödinger equation, where you can define this eigen energy value, En. And the interesting thing is you find actually zero eigenvalue solution exists, which we call it zero mode solutions. And the expression below just tell you the explicit formula of the zero mode solutions. And in the transverse wave function, you show the exponential function shows up, where the wave function will exponentially suppress when you go far away from the string center. And the typical wave function spreading is related to this fermion mass, and also some information from this string profile function, which I will talk about in more detail in next slides. And also the spinor eta for the zero mode now is very different, changed compared to the free fermion solutions. So in summary, fermion zero mode exists in the string background. So let's look at more details of the zero mode solutions. Now let's focusing on the longitudinal directions. And we plug in this explicit solution of spinor eta to this equation motion and reduce to this differential equation of the longitudinal wave function alpha. The first property is that actually the alpha is a solution of the combination of both time and the z coordinate. That means the zero mode actually propagate along the minus z direction at the speed of light. In other words, the zero mode is effectively massless, propagating along the string. Second property is we can further find out the equation motion for the antiparticles by performing the charge conjugation transformation for these zero mode solutions. And in the YO basis, we can find that the spinor, only the spinor is changed under this conjugation transformation. It changes from E eta to minus I times E eta. So plugging back to the same equation motion, you find the alpha wave function still satisfy the same form. That means the antiparticle also move at the same direction as particles. That means in this string background, actually the fermion zero mole is a chiral. They're only moving in one direction. And later you see this chirality, chiral fermion is give you some chiral anomaly or gauge anomaly in 1+1D. That's is the important thing for the superconductivity. And the further property is we can further look at the exponent of this transverse wave function and require the exponent to be order 1. Then you can define the typical wave function spreading. It has two different behavior depending on the hierarchies between the scalar mass and the fermion mass. And when you consider heavy scalar mass limit, it's just given by the constant wavelength of this fermion. But if you take the heavy fermion mass limit, it depends on the geometric mean of both the scalar mass and the fermion mass.
And what is delta sign?
I introduced the spreading, the width of this zero mole wave function. So the width when the amplitude reach to decrease by 1/e. E is the yeah.
Okay, you mean the width off the string?
Yeah, the width of the not the string. The width of the string is
The width
delta.
off the string. The width of the zero mode off the string.
Okay. Okay, something like that.
Of the string center, I guess.
Yeah.
Away from the string center, yeah.
So yeah, this property just tell you zero mole is localized on the string or bound on the string. Okay. Now I want to study. So previously I didn't talk about the gauge charge of the psi. Now introduce some electric charge to this fermion zero mole, and that's will actually tell you how to induce zero mole on the cosmic string. And here I choose one example, simple explanation by using the chiral fermion in 1+1D theory. So here the reason why we can consider 1+1D because as I mentioned before, fermion zero mole is effectively bound on the string. So you can effectively using the 1+1D theory to describe the dynamics of the zero mole. And here suppose the zero mole carry electric charge Q is positive and is moving along the -z directions. And I prepare all the initial state of the zero mole is such that the Fermi energy surface is 0 and all the negative energy state is occupied by this psi. And then after I turn on some electric field along the z directions, and then you can see the electric force fueled by this psi is actually pointing upward. However, the zero mole is moving downward. So you can see the work done by this electric field is negative. That means the Fermi energy will decrease because the kinetic energy of the zero mole is decreasing. So then you find the Fermi number is not conserved for this chiral fermion. And that means the net electric charge induced. And you can further compute the change rate of the linear charge density, lambda q dot, is proportional to the change rate of the Fermi surface. And also by using continuity equation, you can find the current density change rate. And the rate is proportional to applied electric field along the string directions. And then we can compare this equation to the Ohm's law for conductor. So for Ohm's usual conductor, if you apply the electric field, you will have the current. If you turn off the E field, there's no current. But for this zero mole and string bound system, actually, when you turn off the E field, they still have some persistent currents existing. So that in this case, we say this string is superconducting. Okay, the full theory actually need the called the anomaly inflow theory from the 3+1D bulk. Here, I don't have time to explain the whole story, but I list the reference for you if you are interested. And also, Professor Harvey is here. He's from U Chicago, and he make important contribution to this topic. In summary, the string superconductivity can be summarized as zero moles exist on the string background. Zero mole is the charge carrier of the superconducting string, and zero mole can be induced by applying electric field along the string. Now I want to introduce some benchmark model in this talk. we're focusing on the KSVZ type QCD axion model, where the KSVZ fermion is the vector-like quark, and the left and right-handed component carry the different U1 PQ global charge. And for this moment, I assume the hypercharge is arbitrary for this moment. And then suppose in the post-inflationary scenario, you form before the Patrick-Green phase transition, the KSVZ fermion is massless, and it can be abundant in the thermal bath because the thermal contact with standard model thermal bath. And then after the Patrick-Green phase transition, the PQ scale field get non-zero wave and also form axion string, while the KSVZ fermion in the vacuum, they can obtain the masses and become massive particle. And there will be some very important constraint for this KSVZ heavy quark, because after the hadronization, this KSVZ fermion can bond with some standard quark and form some fractionally charged valence. That is extremely stringently constrained by the experiment near the Earth, and the number density of this fractionally charged valence is has to smaller like 10 to the minus 20 times the nuclear number density. In this case, we need to require the hypercharge of the KSVZ fermion to be this minus 1/3 plus integers. And in our paper or talk, we said that Z is 0. So you can consider the KSVZ as like something like down-type quark in the theory. And then this hypercharge actually can induce this coupling between the standard model Higgs and quark. And the coupling is denoted as YD. And using this coupling, you can help the KSVZ fermion to satisfy the BVN bound just by requiring the decay process of the fermion in the vacuum, decay into standard model particle much before BVN. That gives you some lower bound on this decay coupling YD, given in this expression.
Sorry, what's YD? Is this H is the Higgs field there?
Yeah, H is the Higgs and Q is the standard model.
Q is the standard model.
Yeah, Y is some Yukawa line.
Yeah.
Coupling. Yes. So yeah, after you have did this interaction, you will also introduce the decay process of a fermion ZMO when the psi is on the string. And yeah, we will talk about that later.
Doesn't that psi fix what Z is? Doesn't that non-zero having that coupling fix what Z is?
Doesn't this non-cup fix the Z? You mean?
Yeah.
Yeah, the Z can be in integer 0, 1, or.
But I mean, Q L bar times H has some definite.
Oh yeah, you're right. Yeah, here I choose Z is 0. Yeah, thank you. Sorry. Okay, now let's talk about some string dynamics. First, when the closed loop can form when the long string intersect with each other or themselves. When the loops is formed, it will oscillate and shrink due to the string tension. And during the shrinkage or oscillation, you have the axion radiation. And the smaller the loop size, actually the stronger the acceleration of the shrinkage. And after few or several oscillation, actually the string loop will disappear by the radiation of axions. So this is the general picture of non-superconducting string. If the string is superconducting with fermion ZMO propagating along the string loops, then you will have a counterbalance force coming from the Fermi pressure of the ZMOs. So you expect, as long as the fermion ZMO there's no other dissipation process to decrease the number of the total fermion ZMO in the string, then you can expect at some critical size, we call LC, where the string tension is equal to this Fermi pressure of the ZMO. And then you can have after some relaxation process, you have this stationary cosmic string loops we call the vorton. So there are two important quantities for the vorton. One is the critical size, LC, another is the charge of the vorton, Q.
Can I ask some questions about this? So in the first process, so in the collapse,
Yes.
that part, that loop shrinks to a particle. What particle is that at the end?
Actually, it's just not a particle. It just disappear. They become the radiation.
It just becomes radiation.
Yeah.
So the loop itself is not charged under anything?
Not charge. It depends on the phi field. If you
Uh-huh.
depends on the charge of phi field. Yeah, but there's no
But
another
in your
charge
description,
type.
it's not.
Yeah.
And then in the second process that you talked about, do you need some sort of non-zero electric field density to have this stabilizing force?
Yeah.
If the
But
electric
not
field-
exactly electric field. Can also the cut. For example, the color charge. As long as the fermion carries gauge charge, that's fine. Because you need the gauge field, the electric component of the gauge field to
But the Fermi
induce.
pressure that you talked about would require a non-zero density of.
Yeah, non-zero density.
So where does this how is this density sourced? Where does that come from?
Just
In terms
coming
of
from the Nobby inflow I mentioned before. So if in the environment you have some non-zero electric field or electric component of the gauge field that can along the string have some non-zero component along the string direction, then you can induce this zero mode.
But if the ambient, if the ambient state of the 3+1D has, if you're in a region, I guess, where the expectation value of the electric part of the field
Yeah.
is zero, then there is no such pressure, right?
Yeah, right.
Okay.
That's true. But yeah, we want it
Yeah,
non-zero.
I'm just trying to understand. Okay.
Thank you. Yeah, first I want to talk about the vorton charges and how you can induce the zero mode in the early universe. Here we actually focusing on the thermal thermal bath surrounding the cosmic string. And we consider, because the thermal fluctuation of the thermal bath, you have the generic EE field with the amplitude proportional to temperature squared by dimensional basis. And then we consider this thermal fluctuation can be described by a random walk process, such that you can use describe or introduce the coherence length and coherence time for this thermal bath electric field, and they are given by 1 over temperature. And then you suppose there are some initial size of the string loops, which is about 1 Hubble size, the largest string loops. And then we truncate the total strings size into different smaller coherence patches. And then you can find the total length or spatial steps for this random walk is given by this square root of Hubble size divided by the coherence length. And also in the time steps, you also have consider the shrinkage process happen within 1 Hubble time. You can also have this enhancement or accumulation due to the NT time steps. And finally, you can compute the total charges by summing up all the segment and steps. That the result is give you the charge is inverse proportional to the temperature when this loop string is formed. And yeah, and the typical value or benchmark value is at temperature 1 TeV, the total charge is about 10 to the 15 E. Yeah.
I'm being slow. Can you just explain this electric field goes like T squared? Where did that electric field come from? What?
The photon energy density in the thermal bath. So the rho of radiation goes like T to the 4. And the
Which direction does it point?
it's just the amplitude. The direction is random, and within one coherence patches, you can consider it's a constant direction. But the direction is you have some random directions. So you can pointing upward for this coherence patch. In the second coherence patch, you can pointing downward, something like that.
I see.
Yeah, this is just an estimation. It's not.
So the expectation value of E.
Yeah.
Over this purple is the string. What is this purple?
Yeah. Yeah, purple is the string. A carton of string core. Yeah.
String core.
Yeah,
Okay.
core.
The distance across is the core. So like.
Okay.
So on the string is the expectation value of E 0 or not 0? I'm trying to understand this sort of strange. You have this spatially varying E. What is the actual E that the string sees? Like how do you actually run the 2D calculation?
Oh, effectively, we consider the string is very thin, so just a 1D object. So you can consider.
1 + 1 is 2. I meant the, yeah,
Sorry.
yeah.
Okay, 1 + 1 is 2. Okay. Yeah. Okay. Yes.
Yeah, I just mean like how you want to consider the force calculation. In that calculation, you had a definite E that you were using. I'm trying to understand how this kind of wildly fluctuating E
Yeah.
fits into that calculation.
Oh, yeah. In that calculation is here, shows up here. So E is replaced by T squared by just using the fluctuation. Yeah.
It doesn't
You
matter
can
that
get.
the actual E that's being experienced is a discontinuous field on the string. So the actual E that's being experienced is like wildly rotating around as you move.
Yeah, actually, you have the projection angle. Yeah, give you from 0 to 1. Yes, you're right.
So that doesn't matter?
Yeah, I think it matters, but here we just give an estimation, just a root mean square. So the benchmark value you can gain, maybe it's the maximum value you can get. Yeah. The detailed calculation, yeah, is more complicated than this, of course. So if you have this total charges Q, then you can relate it to the Q to the Fermi surface of the theorem. So by just assuming this fermion, the density of state is 1D fermion density of state, and you find the linear charge density proportional to the number density of fermion, and then you relate the linear charge density to Q over L. L is the size of the loop. And you can find the Fermi energy is proportional to Q and inverse proportional to the size of the loop. And the total energy is by summing up all these or integrate along the density of state from energy 0 to Fermi energy. You find the total Fermi energy, total theorem energy is Q squared over L. Okay. Then we want to. Yeah, the second quantity of the vorton is the size of vorton. And here I draw a diagram for the total energy of the vorton as a function of the loop size, L. And different color represent the different formation temperature of the vorton. And here, when it actually you see the two power law behavior. When the L is large, actually the string mass dominant the total energy, where the string mass is linear proportional to the size of loop. So basically the string tension times L. In the small L regions, smaller loops, actually the zero energy dominates because the Fermi energy is inverse proportional to L. So you expect the intercept of these two lines give you the stationary point of where the Fermi energy balance the string mass. Then you attain the critical size, which is given by the number of a fermion total number divided by VA. And here I also draw another solid, dot dash line representing what's the maximum Fermi energy or Fermi surface that the zero mole can reach, such that if the energy is greater than that, or the loop size smaller than that, the Fermi zero mole can become a free state. So they can be, and so if the Fermi surface is large enough, actually the fermion zero mole will not be bound on the string, but can overcome the mass potential in the vacuum and become a free propagation mode. So here I will also explain this, and we derive this by considering the quantum tunneling process of the zero mole industry. Okay, so I'm going to talk about the stability problems. Whether the vorton is stable or not. So I summarized the stability problem into these 4 questions. The first question is we want to ask, because in the previous diagram, I actually neglect the kinetic energy of the loop when it's shrinking. So when we're taking into account the shrinking, the kinetic energy of the loops, will the fermion zero mole will overshoot from this shrinking loop. A second question is I haven't talked about the Fermi energy when the loop size reach to the critical size. So if the vorton reach to the critical size, will this Fermi surface is very large, such that the DMO can just jump out of the string. And this question related to the quantum tunneling process. And the third question is, even the critical Fermi energy is fine. The fermion is not sufficiently tunneling off the string, but the DMO can genetically decay. The decay process will also dissipate the number of the DMO in the string. So we need to ask, what's the decay rate of this DMO? And the last question is also the scattering with the surrounding charge particle will destabilize the vorton. And we need to understand that. So in summary, the vorton stability problem is non-trivial. Okay, let me address the first questions one by one. The first problem we actually related to the classical stability of the vorton. Here I did this diagram using the same diagram, but I here have some little yellow dots which represent the total energy of the loops. So including the string mass and also the kinetic energy. So suppose the initial loop size is 1 Hubble size. So such that the initial mass is also proportional to L. So it's very gigantic. When the loop shrinks to the critical size, if the string total energy, string mass plus kinetic energy is conserved, then you will have a problem because the kinetic energy actually is very gigantic, even though the string mass is very tiny like this. But in order to compensate this gigantic kinetic energy, you may need the Fermi energy with actually reach to this value, where the string loop size is much smaller than this LQT. So in this case, actually the vorton, the DMO already jump out of the string, and you don't have a stable string configuration. To answer this question, whether kinetic energy is such big, we perform the lattice simulation of this axion string for circular loop configuration. And we choose different initial size of the loops. And we found, compare these two cartoons. The first one, there's no axion radiation. You see the string shrinks very fast. Actually, when it reached to the collapse point, it reached the speed of light. However, if with axion radiation, you can see the shrinkage process is is very slow. And finally, we measure the kinetic energy of the shrinking loop with axion radiation near the collapse point, and we found actually the final kinetic energy can be just same order of magnitude of the string mass. So then we are safe. We don't have gigantic kinetic energy because the dissipation through the axion radiation. So then we say in this simulation, we claim there's no evidence of the overshooting of DMO.
So what's being plotted here? The solution to some classical differential equation? What is being plotted?
Yeah, the plot is the field, the phi field configuration.
But
So
the solution to a classical differential equation, is that correct?
Yeah, but yeah, using the potential is the Mexican half potential.
But where do the fermion zero modes go?
Yeah, fermion, there's no fermion DMO in the simulation. So we're just measuring just the dynamic of the string itself.
But I guess I have this question about the whole stability problem in general. So
Okay.
if we have some net density of zero modes
Yes.
on the string, where do they go? I mean,
Oh, where do they go?
you cannot put them in the same state, right? So
Yeah, you can consider depends on, because they are a bound state. The fermion plus string is a bound state. Depends on the time scale for this shrinkage time scale versus the relaxation time scale of the bound state. As long as the relaxation time scale much shorter than this typical shrinkage time scale, then you can assume or just say the bound state they will asymptotically evolve together. Just like you have the potential is like 1D potential problem, and you have the wave function in this in infinity potential valve. And when you change the valve, when you shift the position of the potential valve, you just ask what's the probability of this wave packet will evolve to the new energy eigenstate, something like that. It's just like a quantum mechanical system.
Does the Fermi pressure increase as the
Yeah, the Fermi pressure
as it gets
increase.
smaller?
Yes.
So why doesn't it eventually stop the shrinking?
The shrinkage is because when you shrink to some small value, the string mass also decrease, and as long as the kinetic energy plus the string mass is not so big, then you still have you can shrink to a smaller value here, such that the Fermi energy can balance of both the string mass and the kinetic energy. Then you can.
But I'm asking why
Oscillate.
why doesn't I'm asking about the final state here. You seem to imply that the string completely disappears, but why doesn't the Fermi energy eventually the Fermi pressure eventually stop it?
Oh yes, because you can, for example, you have the range from LC to L quantum tunneling. So
it's
within
because
this range,
once it gets too small, if there's like
The Fermi energy
the
range.
fermions,
the pressure will, yeah.
it's favorable for the fermions to escape the string?
Yeah.
Is that what happens?
If you go below the LQT, the Fermi zero mole will become a free state. As
I
we
see,
said.
okay, so
But if not, then it's fine.
that cuts off the growth of the Fermi pressure.
pressure, yeah.
What you found is because of the action radiation, it string only gradually shrink and never overshoot down to the small radius where the fermion can be kicked out. In this simulation, actually, fermion is not included, but what actually would happen is it's just shrink gradually and stop around the critical radius if we actually include
Okay, so I should not take the zero size limit of that simulation seriously.
in the realistic case.
I see, okay.
Yeah.
Yeah, sorry. Okay. Yeah. Now move on to the decay process. And actually, the second and third question, they are correlated. So we will talk about them together. Second question is related about the critical energy or Fermi energy or the maximum Fermi energy that the zero mole can reach, such that they are not energetically jump out of the string. Here I calculate the critical Fermi energy. It's just by replacing the loop size by the critical size, and you obtain is given by 2 pi VA. VA is the symmetry breaking scale. So first argument is if the Fermi energy is greater than the fermion mass in the vacuum, then zero mole has non-zero probability to jump out of the string. Just you can counter tunneling, or it's already energetically enough. So you have the non-zero probability to become a free state. And then compare the critical energy 2 pi VA versus ampersand. Seems 2 pi VA is generically greater than ampersand. So the vorton is unstable because you have this energetically jumping process. Secondly, in the work done by Barr and Matheson, they divide another value for this maximum Fermi energy, which is given by ampersand times enhancement factor ampersand R, where R is the radius of the vorton, based on the energy momentum conservation of the zero mole between the initial state and final state. Since ampersand times R can be much greater than 1, then since the vorton is stable. Okay, and in our study, we actually studied this process by computing the quantum tunneling rates of the fermion zero mole, and our result actually is in between these two values. I will explain that later. The third question is the decay rates calculation of zero mole, and there are actually 2 studies on that. However, their results are not so not the same. And actually, we find in our formalism we can identify these two processes into two different decay process. In the first process, where the string background actually is stationary or slowly varying, while in the second process, the string oscillation is fast enough, so we need to take into account the non-adiabatic process, or we need to take into account the change of the string background onto the decay of dual. Okay, to study this decay rate, we need to we introduce the string Walsh formalism to compute the decay rate. The idea is simple. Because the dual is localized on the 1D string, we simplify the 3+1D interaction to 1+1D interactions and introduce the effective coupling on the Walsh kappa, where kappa depends on both the decay coupling of fermion and also depends on the wave function spreading in the transverse directions of dual. And here I choose some limits, which you can consider the spreading is given by 1 over ampersand. And then you can simplify the S matrix using the 1+1D coupling of string Walsh.
What is the second line? What is this F per? It was just a little too fast for me.
Oh yeah, sorry. Yeah, F tilde is the transverse wave function of the dual that give you the exponential e to the minus ampersand. Yeah,
Okay.
something. That just tell you the wave function in the transverse direction.
Okay.
And yeah, if you integrate along the transverse direction, it give you dimension like the width.
Fine.
Yeah. And okay, the S matrix in this string Walsh form is simplified to a 2D integral. And the time integral is the usual energy conservation, where the final total energy EF is equal to the dual energy E. And the second part is a spatial integration along the string direction, where the zeta is the string Walsh spatial coordinate.
What are the in and out states that you're computing this with? What is?
Oh yes, the process decay process one psi 0 to standard model quark and Higgs. So it's a 1 to 2 decays. But it's, you can generically consider n body decay.
I see, and that
Yes.
interaction is just the Yukawa.
Yeah,
coupling
Yukawa term. Yeah.
that you talked about before.
Yes.
I see. And the P, I see. So the in state, the
In state is the
P, that's
zero.
where you're using this F. Okay.
Yes.
Mhm.
Okay, thanks. And yeah, the spatial integration is just give you the wave function overlap between the final state plane wave and the initial dual wave function, longitudinal wave function. Okay. First, I'm focusing on the massless final state limits, where you take the two final state mass either 0 or the sum is much smaller than the dual energy, where the n is the quantized angular momentum of the dual, which is equal to the dual energy times the radius of the loops. So it's an integer because the stationary or the periodic condition, binary condition. And then we find actually for this massless two-body final state decay rate is proportional to this three parts. First part is you may be very familiar. If you replace the E to ampersand, it's just the decay rate for fermion in vacuum. And the second part is related to the dual spreading. There's the spreading has suppressions. And the third part is the kinematical for the kinematical reason, where the final state phase space actually is only confined in a small cone with the open angle given by ER to some power. And here for two final state is minus 2/3. And yeah, actually this result is consistent with the first paper. Then if we plug in some benchmark value, we can compute the decay rate for this 1 to 2 process. Here we choose VA is 10 to 10 GV and the vorton formation temperature 1 GV and unit Yukawa coupling y psi, and also decay coupling is saturated by the lower BBN bound. Then we find the typical lifetime of vorton is about 3 months or 1 semester. So then we say vorton is not cosmologically stable. But actually, I only consider the massless case. So what about the massive case? If we go to the opposite limits where the final state is so heavy, actually we found the decay rate has exponentially suppressions. And also there's another term that's coming from the Lorentz factor of the final state. Here, the reason the Lorentz factor shows up is because if you compute the phase space integration, you find the dominant contribution is coming from when the two final states have the same velocity. So when they have the same velocity, you can compute actually the Lorentz factor gamma 1, gamma 2 are equal, and they are given by the initial energy divided by the total sum of the final state. And the second part is very important. Here I just, for simplicity, I would say is a consequence of the angular momentum conservation of this decay process. And I have one slide to explain this in more details. Now for this moment, let's assume this is correct. If we apply this 1-to-2 process to 1-to-1 process, while the final state is the free state of fermion, then we can directly obtain this quantum tunneling wave, have this exponential suppression, where you just replace m1 plus m2 by m plus I. And requiring the exponent to be order 1, you find the maximum Fermi energy, where the quantum tunneling rate is not exponentially suppressed. So then you find the maximum Fermi energy is actually given by square root of m plus I times r times m plus I. So this result actually is different from the result quoted in the Vilenkin and Scheller's textbooks. And we also we are confident about this value by using the semi-classical analysis, by just requiring the energy and angular momentum conservation of the zero mole between initial and final state. We can also get the same result, which is consistent with the S matrix calculations. Okay, this is one slide to explain the approximate angular momentum conservations I referring before. So if you want to understand where the exponential is so up, you need to calculate the S matrix explicitly. And here we focusing on the overlap, the spatial integration, where it's given by the overlap between the zero mole wave function and the final states. And then for circular string loops, you can carry out this integration by replacing the zeta by r times theta. Then you can find actually the result overlap is given by the Bessel function. And the Bessel function, order n is the same integer of the quantized angular momentum of zero mole, which is e times r. While the argument of the Bessel function is given by the total final planar angular momentum, where PFP is the total final momentum projected onto the loop plane. So then if you further consider, because n is basically the number energy level of the zero mole and is much greater than 1. So we take the large n limits, and you get the asymptotic expansion of this Bessel function that give you this exponential function. And so mathematically, you do this way. And physically, you can see actually the exponent depends on the deviation between the initial and final state angular momentum. And that actually tells you for the massless final state, you can have the angular momentum conserved because the P total final momentum sum can equal to the initial energy. But for the massive final state, because the massive final state, they have the non-zero mass. So some of the initial energy will convert it to the mass energy, while so you cannot make the exponent vanish. So you always have some exponential suppression shows up. And Okay, finally, then you find actually for massive final state, this exponent is given by the Lorentz factor by this. The saddle point is given by this value. And the conclusion is just the larger the final state masses, the larger the exponential suppression for decay rate.
I don't understand these words, approximate angular momentum conservation.
It's
angular
approximate. The sense is not the direct delta function.
But why is angular momentum conserved or not? And why would it not be conserved?
Yeah, to me, I would say because it's not
Is it because the string background breaks some of the rotation invariance in the problem? And so
no, the string background just breaks the translation invariance. I don't see.
no, I mean a loop exists in a plane, right? If I rotate it, it's not in the same plane anymore, right? So
yeah, but
that's a different loop, right? So that breaks some of the rotations.
Yes, but in the calculation, I always project the final state momentum on the loop plane. Yeah, maybe you are right. You violate some of the in the perpendicular direction. Oh, sorry. No. Yeah, because actually the precise zero mode is not a particle. So actually the decay position is matter. So you can decay at exactly R equals to capital R, or you can decay at capital R plus the spreading delta psi. That gives you the uncertainty of the angular momentum. So they are not exactly conserved. So classically, you think it's a particle. So the decay position is fixed. But here zero mode is actually a wave. So it has a non-zero probability to decay out of capital R.
Maybe we can rather say uncertainty in the angular momentum.
Yeah, uncertainty.
Because the transverse rate
of wave function.
Angular momentum is of course conserved.
Can you elaborate a little bit? So you mean that we don't know exactly the initial angular momentum of psi naught because it has some width.
Yes,
Right. And then how does that get converted into this exponent? I just want to understand the.
Roughly speaking, if the fermion is exactly at the center of the core without any splitting, it has some definite angular momentum. So then this decay is forbidden. But by picking up the pair of the wave function,
Then the angular momentum has some non-trivial projection into the broken direction.
Broken. Still angular direction, since we consider the completely circular one.
Yeah.
So angular direction is actually conserved even with the string background. Angular momentum around this axis.
Okay.
Yeah, but what you use that angular momentum.
Okay.
The uncertainty in that angular momentum because of that we don't know exact radial position.
We don't know the radius.
Yeah. Because of spread quantum mechanical uncertainty.
Okay.
Yeah, I think I don't have enough time, but quickly mention the non-adiabatic decay process, where actually the background stream potential is varying very quickly, such that the zero mode state doesn't have enough time to respond to the variation of the background. So in this case, you find the stream modulation will mix the zero mode state and the excited state of the fermion, such that you have a new decay process through this Feynman diagram. And the calculation is finally we taking this non-adiabatic approximation, and we try to divide the effective coupling that describe this non-adiabatic decay by integrating all the intermediate excited state psi star, and we obtain this effective Lagrangian. And compare with the usual decay operator, we find the non-adiabatic decay process always suppressed by this delta phi over phi value. So at most, the modulation is always small. We consider some perturbation description. So this term is always next or subdominant compared to the stationary decay process. And using this understanding, we can reproduce, or we have the consistent result with the second paper. Okay, finally, scattering. So because the precise dual mode carry the gauge charge, for example, electric charge, so generically you can scattering with surrounding charge particle. And also more, I'll say there's a worse scenario because actually the dual mode currents can generate very strong electric field along the core, such that the string pair production can happen. So it's how say the pair produced electron positron will inevitably generated along the string core, and the opposite charge particle will bind along the string because the forces, the electric forces, and then they will have a non-zero overlap. And if the overlap is sufficient enough, then the precise dual mode can also be kicked out by the scattering with surrounding electrons. And this is studied in this paper. But however, in using our string formalism, we still find a way to suppress this scattering rate. The key point is to minimize or decrease the typical momentum of these incoming electrons, pair produced electrons. And the idea is just to reduce the string-induced electric field value. Here, the capital E rho is the electric field induced by the dual mode current along the radial directions. And the typical value is given by VA over the spreading of the wave function. And typically is much smaller than VA squared. So we found by taking the square root of the electric field, we attain the typical momentum of the electron as usually is smaller than the initial, the dual mode energy. And then we can plug in back to the S matrix. And now for the scattering process, different from the decay process, is a 2-2 process. Now, instead of final state planar momentum, you also need to minus the initial electron kick. So after some calculation, you find exponential shows up when you satisfy the ampersand square much greater than the electron momentum times the dual mode and Fermi energy. I will skip this. So basically, you by changing the spreading in different limits, we found actually in the small scalar mass limits, we can, just as long as we make the M phi small enough, we can always satisfy this condition. So then the vorton can still be saved. The final scattering process, another scattering process is coming from the thermoplasma scattering. And here is one example. In this scattering, actually, there's no massive final state. The final state is just a standard model quark and gluon, for example. And then you find the scattering rate is not exponentially suppressed. But the good thing is actually scattering rate depends on the temperature of the thermobath. So we can always choose a smaller temperature such that this scattering with surrounding thermoplasma is freeze out. And then we compute the freeze out temperature. The typical value is about 10 to the 6 GeV for the benchmark value we have here. As long as the temperature, we consider the vorton formed after this freeze out temperature, then this scattering is irrelevant. So the vorton can still be saved. Finally, in summary, this is summarize the dual mode dynamics, the decay process in the left plot, and also a scattering process in the right plot. And this one I didn't mention, but it's very important because it changed the string evolution, where the string-induced magnetic field can scattering with surrounding plasma charge particle, such that the string will delay to enter the scaling region. Okay, in summary, in this talk, I try to address all the stability problem associated with vortons, and we classify into two levels. The first one is classical level. We perform the lattice simulation to support the superconducting string can be relaxed to a vorton by axion radiation. And then we turn into the thermodynamics and talk about the quantum stability of vortons. And we explore the compute the quantum turning rate and obtain the maximal Fermi energy, which is given by this value. And we also consider the decay rates calculation, and it's typically suppressed by the somehow law of the radius of a vorton. And also importantly, it's experimentally suppressed if the final state is measured. Finally, we talk about scattering process, and they can be either irrelevant or efficient by choosing the appropriate value of the fermion and scalar mass. Okay, and the final thing is now we see the vorton can be cosmologically stable. And how about making it to 100% dark matter? That's all. Thank you.
If action is massive, then this
Picture.
proton would not have linearly. It will have a membrane stretch.
Yeah, domain wall.
Domain wall.
Yeah, you form, but the domain wall in this case, because the vorton is the size, the radius is so tiny, you don't have a very thin domain wall. Actually, it's a fluffy wall. So it's not the and yeah, we think the wall tension that doesn't it's not that significant to change the water, because most of the energy density is stored by thermal and yeah. But yeah, that's another thing. Yeah, we can study the domain wall plus vorton configurations.
If there are no more questions, let's thank our speaker again.
Oh, question. You don't see this, you know, guys?